In this example, I'm going to give you the conceptual overview of how to do this type of transportation problem where you want to minimize the amount of gas that you use in order to get from Orlando to New York. And you have two options for getting from Orlando to New York. Number one, you can go straight from Orlando to New York, or you can go to Orlando, go from Orlando to Nashville, and then from Nashville to New York. Now, this has been formulated to be a simple, intuitive problem. So clearly, in real life, it's a no-brainer that you wouldn't, go to Nashville for no reason and then go from Nashville to New York. That wouldn't minimize gas. That would be unnecessary, that trip to Nashville. So clearly, the right answer is to go from Orlando straight to New York. But we want to use this simple example in order to formulate the linear programming problem so you can do more complex examples later on. So as you see, we've got three nodes. Orlando is node 1, Nashville is node 2, New York is node 3. You've got the gallons used to get from Orlando to Nashville is 120 gallons. From Nashville to New York is 80 gallons. If you go straight from Orlando to New York, you use 150 gallons. The first thing we have to do in formulating this problem is we have to identify each city with an index number, because linear programming only works in quantitative environments. So Orlando, whenever you see 1, you think Orlando. Whenever you see 2, you think Nashville. And whenever you see 3, you think New York. So then what we do is we formulate the possible routes we can take to get from Orlando to New York using these origins, these index numbers, as both origins and destinations. So for example, the origin for the first path we could elect to take would be to go from origin 1 to destination 2. Node 1 is Orlando, destination 2 is Nashville. That would take 120 gallons of gas. The linear program will put a 1 here if we're going to take that path, and if we're not going to take that path, it'll put a 0 there. The second path we can take is to use Nashville as an origin, and then New York, node 3, as a destination. So we could go 2 to 3 as another path in this journey that we're taking. And then the last path on the diagram is this line here, from Orlando to New York. 1 to 3. Orlando is 1, New York is 3. That takes 150 gallons of gas. So that so if we were to take that path, there would be a 1 placed right there. Okay, so let's just look at the different options. We could go from origin 1 to origin 2 to destination 2, which is Orlando to Nashville. And so I'm going to put a 1 in there for taking that path. And then we could go from, then we would have to go from 2 to 3. We would have to go from Nashville to New York. So I'm going to put a 1 there for that. Okay, and then of course we're not taking the Orlando to New York path in this hypothetical manual solution we're doing. What that generates is a gallons used of 200. In fact, you can look at it intuitively here and see from Orlando to Nashville is 120 gallons and Nashville to New York is 80 gallons. So that's the one option. The other option is don't go to Nashville at all. Just go straight from Orlando to New York. So we're going to put a 1 there. If we do that, that gives us 150 gallons of gas used, which is less than the 200 we calculated previously. So this is the optimal solution, to go from node 1 to node 3. That's how the linear program is going to solve it. Now the part that needs explanation here is the constraint, because you can't have a linear program without a constraint. You have to understand the concept of a flow. If you leave a node, that creates an outflow of 1. If you enter a node, that contains an inflow of 1. And then if you leave another node, if you go out of Nashville, that also creates a flow of 1. And if you go into New York, that creates a flow of 1. Think about the 1 being your 1 car, going out of Orlando into Nashville, and then out of Nashville and then into New York, or out of Orlando and into New York. There are constraints on that. For example, you must have a net outflow of 1 out of Orlando. You've got to leave Orlando somewhere, either by going that way or from Orlando to Nashville, or going from Orlando to New York. Okay, so that's a constraint, that it must be equal to 1. The net inflow and outflow for Nashville must be 0, because if you do take Nashville, you have to have an inflow of 1 into Nashville because your car entered Nashville, and then you need to have another outflow of 1 as you leave for New York. So 1 in minus 1 out gives you a net flow of 0. And then the number 3 is you must have an inflow of 1 for New York in this model, because you have to get to New York eventually. Okay, so an outflow of 1 from Orlando is mandatory, and an inflow of 1 to New York is mandatory. And if the model does want you to go to Nashville, there must be a net outflow of 0, 1 unit in and 1 unit out. Okay, so that's why we have these required values here. How we get the left-hand side is by using a SUMIF function. What we do is we go SUMIF for all of this column right here, and let's just say that this was the solution we're working off here. Okay, we would go SUMIF, and SUMIF, what you do is you look at this array here and you add up this column if the corresponding value to each one of these values here is node 1, which is Orlando. So you can see that it looked here. It looked all the way across here, and it looked across here, and it said, okay, there's 2 places where 1 is represented, here and here. And then it went over here and it added 0 plus 1. This 0 corresponds to this 1. This 1 corresponds to this 1. So 0 plus 1 is 1. Okay, that's the first SUMIF you do. The second SUMIF is a double SUMIF. If you look right here, it's up, the formula is up here at the top. What it did is it goes into the origin and it adds up all of the values in this flow column based on whether or not there's a 2 here. And in this case, it went through and said, okay, we've got 1, 2, and it's a 0. So we're going to add that up, and we're going to remember that. So 0 is the first calculation that it remembers. And then what it does is it goes in the destination column, and if there's a 2, it adds up the value associated with the 2, which is Nashville, and it puts that value there, which is 0 as well. So we're taking each of these SUMIF results, and then we're subtracting the second one from the first one, which gives us 0. See, if the solution, it's not, but if the solution was go from Orlando to Nashville from 1 to 2, and then from 2 to 3, you see how what this would have done is it would have looked into the origin column and said, oh, there's a 2. It happened once, so in that column associated with that, there's a 1, so it's going to put a 1 there. And then it's going to go into this column and look for a 2 and see what the associated flow is, and that's a 1 as well, and it's going to put that there. 1 minus 1 is 0, and that satisfies this constraint that the value going into Nashville must be equal to the value going out of it, because Nashville is just a transition point. Okay, then the last thing it does is it uses the SUMIF function again, but it does it on the destination column. So let me just change this, 0, 0, say this is the optimal solution. I'm just making this up, but I say that's the optimal solution. What it would do is it would go through, we use a SUMIF formula where we say go into this column right here, check to see if there's any 3's in it, and if there are, add up their associated flow. So what it would do is it would take this 0, which is associated with 3, which is New York, and we would then see another 3, and there would be a 1, and then it would add all that up, and you would find out that the flow, overall net flow, is 1 from Orlando, New York, and it put the 1 right there, which satisfies this constraint that it's got to be equal to 1. Okay, So that's the hardest part, is recognizing that you have to use the sum if function to make sure that you've got at least one outflow from Orlando, which is node 1. You've got to have a net flow of 0, meaning you go into Nashville and out of Nashville, and you've got to have one inflow equal to 1, indicating that you're going into New York. That's the requirement. And the gallons used is going to be another sum product function, D4 to D26, D4 this, multiplied by, and it should be E4 to E26, this. Take the number of gallons multiplied by whether the route was taken to come up with your total gallons used. Okay, so let's solve this problem now. What we do is we go to Data, we go to Solver, we want to set D35 to, by changing these values here, subject to these constraints, and C31 must be equal to E31. C31 right here must be equal to E31. C32 must be equal to E32, and C33 must be equal to E33. So all we're doing is making sure that the net in or outflow from each node is equal to what's required. So you click on Solve. Oh, okay. And objective cell must be a single cell. Okay, this happens sometimes, so I'm not upset that it occurred. You see what happened here? For some reason, this can get off. The objective cell was the gallons used. Somehow when I was clicking around here, I inadvertently reset that. So we click on Solve, and it found a solution. We click on OK. To identify the optimal solution, we see that the path taken was this one right here. A 1 was next to going from node 1 to node 3, from Orlando to New York. That's the most efficient route to get from Orlando to New York. And you can see that the gallons used is 150 gallons, which is the minimum. And we were able to determine that intuitively. But you will see in other problems that you will have a lot more origins and a lot more destinations and a lot more paths to choose from, to the point that you can't really tell just by looking at it. You need this linear program set up in this way in order for you to be able to come up with the optimal solution. And that's the concept of what the homework number 1 is all about.